Hi, in this video we're going to look at the Maths Admissions Test from 2018 for Oxford, Imperial and Warwick, in particular question 4, which is for people applying for Maths and Statistics or Maths and Philosophy. So computer scientists don't do this question, they do the later ones instead. Please do like the video and subscribe to the channel if you're finding them useful, and I always like to hear what you're up to in the comments, so let me know what stage of maths you're at and if there's anything else you'd find useful. And there's a whole playlist of these videos going through the whole paper, and I'll link that below as well. So let's get on with question 4, and this one is a geometry question, not everyone's favourite, but I think although it can be tricky to identify what you have to do in these questions, there are only a really finite number of theorems to do with geometry that you have at GCSE and at A level, and usually these questions are going to be slightly tricky applications of those simple theorems. So they're going to ask you to apply the basics just in a more complicated way, and we'll see how that pans out here. Okay, so it says here we've got two overlapping circles, S1, which is the larger circle here, and S2, the smaller one, and they've got a radii of √6 and √3 - 1 respectively. So first trick in circles, always remember to look out for radii wherever they appear. So I know this length is √6 AE, so automatically I know AC is √6, AD if I need it as √6, etc. So yeah, the other one is √3 - 1, and they're going to intersect at these 2 points C and D, and the two centres here, A and B, are 2 units apart. And it says here the sketch below is not to scale, so we're not going to expect this to guide us too much apart from in the kind of sort of geometry of where the points are relative to one another. And part 1, it says find the angle CBA, so that's this angle here of course, and deduce that A and B lie on the same side of the line CD. So there's a hint here, okay, the diagram is sufficiently to scale, I guess, that they've drawn these on the right side of the line, but really, if the diagram's not to scale, we can't assume that in advance. So I think really the best thing to do with these sorts of questions, just redraw the particular triangle or the particular part of the picture we're looking at here. So here I'm going to draw the triangle CBA. Okay, and I want this angle CBA here, so I'm going to call that one X. Now, as I said about the radii, this one BC is a radius of S2, so it's got length √3 - 1. AB is 2, that's told to us, and AC is also a radius of the larger circle, so that's got length √6. And now hopefully once you've drawn that triangle, it's clear that you can apply the cosine rule here, and just use that to find x. Okay, so we've got the cosine rule that says that a squared is b squared plus c squared minus 2bc cosine a, and I'll just substitute the appropriate values in here. So a has to be √6, and b and c can be either way around, so 2 squared plus √3 - 1 squared minus 2 times b times c, so 2 times 2 times √3 - 1 times cosine of x. So if we just sort out the numbers here, √6 squared is 6, and I've got 4, √3 - 1 squared, so that gives me 3 plus 1 minus 2 √3, and then here I've got minus 4 times √3 - 1 times cos x. Of course, in the real thing you might want to do this slightly more quickly than I'm going through it, but do show enough working to make your answers clear. So I've got here, if I subtract the 8 and the 2 √3 from both sides here, the minus 2 √3, sorry, I get minus 2 plus 2 √3 is 4 times √3 - 1 times cos x. So the left hand side here factorizes as 2 times minus 2 times well, I can do it as minus 2 times 1 minus √3, I suppose. Let's just write it like that. is equal to 4 times root 3 minus 1 times cos x. Oh, and I've lost the minus here. There was a minus in front of the 4, so I should have to keep that in here. So if I divide by root 3 minus 1, 1 minus root 3 is just minus that. So we just get that cos x here is equal to minus 1/2, also dividing by the 4. And you should be able to work out, if you need to draw a little graph of cosine, that if cos x is minus 1/2, then that means x is equal to 120 degrees. If you're studying this paper, hopefully you can make that step. And now the last part of the question says, deduce that A and B lie on the same side of the line CD. Well, this angle here we found is 120 degrees, so it's bigger than, in particular, it's bigger than 90 degrees. If the angle was smaller than 90 degrees, it might have been over here, but that means that both A and B are to the left of the line CD. Okay, so I'm going to say that 120 is bigger than 90 degrees. So A and B are both to the left of CD, and that's the first part of the question done. Okay, so not too bad so far. What does it say next? Okay, so we've got to show now that CD has length 3 minus root 3, and hence calculate the angle CAD. So we've got a choice here. You know, I've got a triangle CBD and also triangle CAD, and in principle we could use either of those to work out CD perhaps. But remember, we've just, in the last part of the question, if I let me add in an extra line in here, I'll do it in a different color so you can see it's extra parts that we've worked out. So this one that we just worked out in here was 120 degrees. So if I use triangle CBD, I've immediately got an angle that would be useful. So I'm going to start by doing that. So let's just redraw that triangle CBD, and again we can see that CBD is an isosceles triangle. Okay, so actually if I put a line across here as well, then okay, we know that because CBA is 120, this part in here must be 60 degrees. Okay, and we also know that this length is root 3 minus 1, so the side that I want is CD. So if this is x, then this is also x. So this is half of the length we want because of the isosceles triangle, and then this is just easy to work out, right? X, just by ordinary trigonometry, is root 3 minus 1 times sine of 60, which is root 3 minus 1 times root 3 over 2, and so actually if I wanted 2x, then that will cancel the 2 from the fraction, and that'll just be root 3 times root 3 minus 1, which is 3 minus root 3. I might say here as required, just to show that I've got to the point in the question where we had an answer given. And then it says, hence calculate the angle CAD. Okay, so now I do need to go to my other triangle, C. So let's have a look at that one as well. Again, I'm just going to redraw it nice and clearly on its own, so I can see it. This is going to be CAD. Okay, so we've just worked out CD is 3 minus root 3, CA is root 6, and AD is also root 6 because they're both radii of the circle there. And I want CAD. Okay, so let's call that one theta. And so again, I can just apply the cosine rule here again and work out theta as we did before. In principle, you could also try splitting this in two and working out 1/2 of theta. If you do that, you'll see the numbers don't necessarily give you such an easy angle to work out if you go down that route. So I'm going to stick with the cosine rule here. So again, just as before, so 3 minus root 3 squared here is going to be root 6 squared plus root 6 squared minus 2 times root 6 times cosine of theta. So if I multiply all of this out, I get 9 plus 3 minus 6 root 3 is equal to 6 plus 6, so 12. minus 12 times cos theta. So I get the 12s here cancelling out. So I have that cos theta is minus 6 root 3 divided by minus 12. So cos theta is root 3 over 2. And that gives us that theta is 30 degrees here. Okay. And notice, when they said this diagram was not drawn to scale, they were not lying. This does not look like 30 degrees at all on the picture, but we have found that to be the case. Okay, so hopefully not too bad up to this point. It's obviously going to get more challenging as we go on. So part 3, it says, show that the area of the region lying inside the circle S2 and outside of the circle S1, so the shaded region in the picture, is equal to pi over 6 times 5 minus 4 root 3 plus 3 minus root 3. Okay, so obviously I've got to find some strategy as to how I get to this this shaded part. Now, if you remember doing segments and things, GCSE, you know the sort of thing we're going to have to do here is, to try and, I want to sort of try and take a sector and then get rid of the triangle. So, that would give us this whole segment here, but it's not exactly, a segment. So we have to try and adapt that methodology here. And so one way to do this, clearly you can look at this and say, well, it obviously involves like this sector, maybe these triangles in here somehow. So I want to include the this part, the shaded part. So I'm going to start with, I think, sector CBD. Okay. So that's going to give me this and this. Now, I don't want this part here kind of in CBD, but that's a slightly awkward shape. So what I'll do, I think, is I'll subtract the whole sector CAD. There might be slightly different ways you can go about this. Now what have I got here then? So I have now got this part, okay, and I've subtracted. Okay, let me add in another line here. Okay, so I've now so I added in this bit to begin with, and I've also now subtracted it, okay, but I've also along the way subtracted these parts here, okay, so I actually need to add back in those two triangles, because at the moment I've got minus those two triangles. So let's say I want to add in 2 times the triangle CAB, okay, because CAB and BAD are congruent, so I can just do one of them twice. Okay, so actually that bit takes the most time. I haven't written that very much down yet, but I've got the whole strategy now, and I'm pretty confident that I can just follow this through by plugging in the numbers, and we should be able to work it into this formula. Okay, so the sector CBD, okay, well, we worked out before that that angle CBD in the first part of the question was 120 degrees. Okay, so that's one third of the circle, and the circle that has radius root 3 minus 1, so just pi times r squared. I'm going to subtract sector CAD. Now we just worked out that that is only 30 degrees, so that's 1/12 of a circle whose radius is root 6, so pi times root 6 squared. And then for triangle CAB, the CAB here, if we go back to thinking back to the first question, again we had that was root 6. We've got that as 2, that's root 3 minus 1, and the angle in here was also 120 degrees. So I've just got 2 lots of the triangle. A half AB sine theta is the rule we'll use here, so 2 times a half times 2 times root 3 minus 1 times sine of 120. Okay, so I now just need to sort all this stuff out. So I've got 1/3 pi root 3 minus 1 squared, so 3 plus 1 is 4 minus 2 root 3, half times root 6 squared. Oh, sorry, that was not a half, is it? That's a 12th. I said it's a 30 degree angle, so this is 1/12 of the circle, so a 12th times 6 is a half, so I've got minus 1/2 pi, and then 2 times a half is 1, so I've just got 2 times root 3 minus 1 times sine 120, so 2 root 3 minus 1. Now sine of 120 is root 3 over 2. Again, if you need to just plot out this graph and say, okay, I know sine 60 is the same as sine of 120 by symmetry. Hopefully you're pretty good at that sort of stuff. We get root 3 over 2. So actually, so the 2's cancel there as well. Now the form of the answer, it's got this bits with pi factorized out. So I've got a third and a half here. As you can see, they put it as pi over 6. So I'll just get that factorization correct here. So this one is the same as pi over 6 times 2 lots of what's in this bracket. So that's 8 minus 4 root 3. Okay, and then a half pi would be pi over 6 times 3. So I would then subtract 3. And then this is just, if I multiply this out, 3 minus root 3. And then we get to where we need to be, because this is pi over 6 times 5 minus 4 root 3 plus 3 minus root 3. Okay, so a bit of a complicated looking answer, but actually if you just try and do this as routinely as you can and plug away at everything very carefully, then the given answer must come out. Right, okay, last part of the question. It says, okay, now suppose that a line through C is drawn such the total area covered by S1 and S2 is split into 2 equal areas. Okay, so you can see the line that they've drawn here that goes down to E. It says let E be the intersection of this line with S1 and S be the angle, sorry, X be the angle CAE. So actually all this time I've used X in other parts of the question. I probably shouldn't have done because there's an X already in here, but it doesn't matter too much. We're now talking about this X. We may assume that E lies on the larger arc CD, so it is over here somewhere. Write down an equation which X satisfies and explain why there is a unique solution X. Notice here they don't say that we have to find X at all, which implies that we're probably looking for quite a complicated equation, not one we'd necessarily expect to be able to solve, and we just have to explain why it must be possible to find a unique solution by some argument here. Right, so, okay, so this line here, this dotted line along here, let me just, I'm going to draw over that just for emphasis. This is the line we're looking at. That's to split the total area in this whole diagram into 2 parts. Okay, so now firstly let's think about what the total area is then. Okay, well in the previous part we worked out the shaded area, and the total area is just the shaded area plus this large circle S1. Okay, so the shaded area was equal to, I've got it written down here, pi over 6 times 5 minus 4 root 3 plus 3 minus root 3, and the circle S1 is just pi times root 6 squared, pi r squared, so it's just plus 6 pi. And we might just do what they did in the previous part of the question here and bring the pi's together. So 6 pi is 36 pi over 6, so I could put that into the brackets over this side and add 36 to the 5 to get 41. And that's a nice form for the total area. Notice you can do part 4 here, or at least have a go at part 4, even if you haven't done the previous parts. That's the nice thing when they give you the answers and say show that, although sometimes it can mean you have to be more careful with your working. It also means you can do the rest of the question even if you miss some parts along the way. Okay, so that's the total area. Now, so I can do one of 2 things. I can either try and look at the area to the right of this line in terms of X, or to the left of this line. Principle both ways could work here. I think slightly simpler to look at the left side of the line here. So okay, so let's say the left of the line, the left of CE, the area. I've got a triangle CAE. Okay, and then I've got this sector. Okay, I'll call it the major sector CAE. Okay, because usually if you think of the sector CAE, it means this side. Strictly speaking, we should say minor sector and major sector for the smaller and the larger ones. Okay, so the triangle CAE is just going to be, again, we use the half AB sine C formula, so I just got a half times root 6 times root 6. Okay, so I've got these two sides here, times sine of this angle, which is sine of x, and then the major sector CAE, well, if that's x, that's 360 minus x. Okay, so I've got to do 360 minus x over 360 times pi times the radius squared here, so pi times root 6 squared. So I get here 3 sine x, and I don't think you need to do too much simplifying here really, but why not just do a little bit. 360 minus x over, I've got 6 here and a 360, so I could write 60 times pi. Okay, so we're almost there. I've just got to write down an equation that x satisfies, so I need this area to the left to be 1/2 of the total. Okay, so I can just say 3 sine x plus 360 minus x over 60 times pi is equal to 1/2 times the total area, pi over 6, times 41 minus 4 root 3 plus 3 minus root 3. And, you know, I mean, I could multiply out the half, I suppose, but I've got an equation that x satisfies, and I think that's good enough here. You know, we're not going to get a huge simplification. Out of this, we can see we've got a very complicated equation to solve. You know, we've got sine x and an x and a constant term here, so not something we can solve easily without a lot of thought. What we do have to do though is explain why there is a unique solution, and you can do this from the geometry of the situation rather than trying to analyze the equation too much. So what we're going to do is think about, okay, the fact that if I take this, you know, this green line, you know, and if I let's say I made x smaller, okay, so in fact, let's do it in a different color here. So let's say I put the x over here and it was smaller, right? You can see that the area to the left of the line is larger, right? And the larger I make x, right, the smaller the area to the you know, above the line here was to the left. Now it's just above the line is getting, right? So so we can say now, and clearly, you know, if I make this line sufficiently far over here as well, I mean, it tells us it has to be at least CD, but you know, clearly it starts at something smaller than a half of the total. So you know, so we can say there is a unique solution. So of course there is a solution because it starts at less than a half and gets to more than a half, and there's a unique solution because, you know, this is going to be continuously increasing in x. Sorry, the area to the left here is going to be continuously decreasing in x as we increase x. Okay, so so you just have to say something to that effect. So the area to the left of CE is decreasing in x. If you're doing this in the exam, I'd advise writing a few more words than that just to spell it out, but I've explained it as I was talking through it there. Okay, so that's the end of question 4. I hope that was useful. These geometry questions can be a little bit tricky just to get your head around what's going on, but if you just don't try and write too much too soon, have a look at it, take a sort of step back from the question, work out which parts of the image are relevant. I'm a big fan of writing down a few things in words just to make what you're doing really clear in case you get a bit of a mistake here as well, and I think it helps you just frame your thoughts about the question as well. And then hopefully this thing should drop out. Okay, so please do like the videos, subscribe to the channel if you found it useful. Let me know in the comments if there's anything I should like me to do, or you know, I'd like to hear what you guys are up to. So tell me what you're doing in maths, and I'll try to reply to all the comments if I can. I'll keep making these videos, and so I will see you in the next one for question 5.